Hello everyone, welcome to another video lecture in linear algebra. For this lesson, we will be learning about non-singular matrices, which are matrices that are generalizations of elements which has multiplicative inverse. To begin with the definition, we would like to introduce some important notations. Here, if m and n are positive integers, the symbol capital M, subscripts little m and n, parenthesis f, or simply mn, mmn, is the set of all m by n matrices over f. So the elements of this set are the matrices of size m by n, m rows and columns, whose entries are all coming from f. If f is clear from the context, we shall drop capital F and simply write m sub m little m comma little n. In the case where the rows and the number of rows and the number of columns of the matrices are equal, we denote the set of all such matrices as m subscript n parenthesis f, or simply big M subscript little n if f is clear from the context. We call the matrices with equal number of rows and columns as square matrices. Let's now turn to the definition of a non-singular matrix. So in this definition, our matrix A is a square matrix. We say that a matrix A, or a square matrix A, is non-singular, or otherwise known as invertible matrices, if you can find a pair, another matrix B, which is also of the same size, n by n, so that when you multiply A times B or B times A together, we will get the identity matrix as the matrix product. This is why it is important that A is a square matrix so that these multiplications can be performed. Remember, AB may not necessarily be the same as the matrix B times A. If this matrix B does not exist, we say that A is singular. In other words, the opposite or the negation of being non-singular is being singular, and vice versa. We first remark that if a matrix B in this equation exists, or if we can find a matrix B that satisfies this for a given matrix A, then this matrix B is necessarily unique. To prove the uniqueness, we suppose that there are matrices B and B hat that satisfy the given equation for X. For example, if you put B in the place of X, or B hat in the place of X, then this equation holds. Suppose that this holds for B and B hat. Our goal is to prove that B is actually equal to B hat because we wanted to prove the uniqueness of B whenever it exists. Notice that B hat can also be written as B hat times In, as In is the identity n by n matrix. Now, because B satisfies this equation, then we can say that A times B is equal to In. Therefore, this In was replaced by the product AB. Now, because matrix multiplication is associative, we can put or place the parentheses over here. Also, because B hat satisfies this equation, then when you look at the second equation, this implies that B hat times A is equal to I, or the identity. Therefore, we can write this product as the identity n by n matrix In times B. Finally, this is equal to B. So what happened is that whenever there are matrices B and B hat that satisfy this equation, then actually they are just the same. So, at this point, The unique matrix B, if it exists, that satisfies this equation is called the inverse of A, and it will be denoted by the symbol A uh, with an exponent of -1. Take note that -1 is not really an exponent. This is more like a notation denoting that we would like to find the inverse of A. As a quick example, let's consider the identity matrix IN. Notice that the identity matrix IN is non-singular. In fact, its inverse is itself, because if you multiply IN with itself, we also get IN as the product. No? Therefore, the element or the matrix which when multiplied to IN is IN is the matrix IN itself. Therefore, IN is an example of a self-inverse matrix. On the other hand, the zero matrix 0n or ON, sometimes 0n, it depends on the book. This is the n by n matrix with zeros as its entries. Then this matrix with zeros as entries is singular. Why? Because any matrix, when multiplied to the 0 n by n matrix, is also the 0 n by n matrix, and this cannot be the same as the identity matrix. By the way, in this context, all the matrices that I'm talking about are square matrices. Let's consider a 2 by 2 matrix A, which has entries 1, 3, 1, 4, and so on. No, this is just a 2 by 2 matrix, I'm sorry. First row is 1, 3, second row is 1, 4. Okay? Our goal is to determine whether this matrix is non-singular. To say that it is non-singular, we mean that we can find a matrix B of the same size, 2 by 2, so that this product actually holds. Looking at the first equation, AB equals I2, then performing the operation, you see that when the matrices on the left are multiplied, like so, it gives us this product. You can verify that this is the product by doing matrix multiplication accordingly. Equating entries, respective entries, I mean 1, 1 entry to 1, 1 entry, 1, 2 entry to 1, 2 entry, and so on, we have the following set of equations. Notice that the first column, so when you look at the first column, it corresponds to the first linear system in the unknowns A and C. When you look at the second columns, this gives us the second linear system in the unknowns B and D. Notice that these linear systems are both 2 by 2 matrices. The augmented matrices of these linear systems are as follows. Notice that the coefficient matrix over here and the coefficient matrix over here are just the same. So to solve this linear system, we should run the Gauss-Jordan algorithm. But because the coefficient matrices are the same, we could actually run two Gauss-Jordan algorithms as into one. No, I mean, we could simultaneously solve this linear system by setting up this particular matrix. Because this is to avoid repeating the process that we need to transform this into RREF and also this matrix. So this particular matrix will simplify the solution for each one of these two. Instead of doing two Gauss-Jordan algorithms, then we can somehow make the process shorter by solving this simultaneously as shown. As you can see over here, this column corresponds to this column, and this column corresponds to this column. As you can see, on the right-hand side of the vertical line, you see the identity 2 by 2 matrix. So we now run the Gauss-Jordan algorithm. In fact, I've done the calculation for you. As it turned out, in this example, this matrix reduces to this matrix as a matrix in RR, EF. So, what we have now are two linear systems, reduced linear systems, which are as shown. Remember that these columns, columns correspond to the variables A and C, and these columns, I mean, correspond to the unknowns B and D. When you look at these linear systems or reduced linear systems, you see that the value of A is 4, no? I mean, because of this, no? A is 4 and C is negative 1. Also, B is minus 3 and D should be 1. So if the equation A times B equals IN works, then we have the conclusion that little a should be 4, little c should be negative 1, little b should be negative 3, and little d should be 1. And therefore, the matrix B that we need is the matrix 4 minus 3 minus 1, 1. This gives us the inverse of A. Take note also that this matrix B, or the inverse of A, happened to be the one which is right here. Do you notice anything? Take note that this algorithm can be generalized as follows. So to find A inverse, given a matrix A of the size n by m, we first set up the matrix A, and then we put a line, and then we put the identity n by n matrix over here, and then reduce it using elementary row operations to a matrix in RREF. Now, if it happens that the RREF of this matrix is the matrix as shown, now IN, and then whatever this matrix is, that matrix should be the inverse of A. And it follows from this algorithm that if you have an n by n matrix A is non-singular if and only if it reduces to the identity matrix as its RR, EF, because of this portion. Now, after performing elementary row operations, then you will be having an inverse if and only if this matrix reduces to the identity matrix. So this gives us a necessary and sufficient condition for a matrix to be non-singular, or for a matrix to have an inverse. As quick example, so let's consider this 3 by 3 matrix as shown. Now, to find whether A inverse exists, we apply this Gauss-Jordan algorithm by appending or putting or gluing the identity matrix to the right of the matrix A as shown on the board. So this is the identity 3 by 3 matrix. This is the matrix A. Now what we do now is we do elementary row operations to transform this matrix into a matrix in RREF. I have done the calculations for you so that we will not spend most of the time doing row reductions in this video lecture. I want you to verify this calculation by hand, or if you want, you can use your softwares to calculate the RREF themselves. As you can see, the left-hand side of the vertical bar reduces to the identity matrix. Therefore, as a conclusion, A is non-singular. And whatever the matrix that is going to be here should be the inverse of A. Therefore, A inverse is given as shown. Take note that you can verify that your answer is correct. Now, how do you verify? How do we verify if we get the correct answer. So this is our question. You can verify that by simply multiplying A times A inverse or A inverse times A. In any of these equations, you should be getting the identity 3 by 3 matrix. I want you to perform, or I want you to multiply A times this matrix, or this and this matrix times this matrix, and verify that the resulting product is the identity matrix. We'll not be doing this in this video, maybe in the live sessions. Let's try to verify it by hand. For the second example, we will do the same. So we glue or we paste the identity matrix on the right hand side and then try to do row reduction and have the following. As you can see, the matrix A did not reduce to the identity matrix. This is not the identity matrix. In fact, in here, no, on the left hand side, we get a 0 row in the row reduction. We only have 2 pivots. Therefore, as a conclusion, the matrix A cannot be non-singular. Therefore, it is singular. Now, this matrix, you cannot, this has no use, or there is no interpretation for this for now. So we just ignore it and just conclude that A is singular. Remember, if A is singular, it means that the inverse does not really exist. So unlike in the real number system or in the field of complex numbers, if you want, take note, in the ring of, or in the field of complex numbers, all the elements, as long as it is not 0, have their corresponding multiplicative inverse. This can be obtained by simply performing the reciprocal of the number. In the case of matrices, however, a matrix can be non-zero, yet it can have, or it is possible that it still does not have a multiplicative inverse. However, take note that A inverse, A inverse is not the same as 1 over A. I saw some, or many students before, that mistakenly writes or identifies A inverse to 1 over A. First of all, the expression on the right is not defined in whenever A is a matrix. We cannot divide a scalar with a matrix. This does not make sense. All right? Although we have A inverse, this doesn't mean that we have reciprocals for matrices. We only do this when we talk about numbers. Now, these are some of the properties of non-singular matrices that we have collected. So, of course, if A is non-singular, its inverse is also non-singular, and the inverse of its inverse is going to be A. This is because the inverse of a matrix is unique. If A times A inverse, or A inverse times A happen to be the identity matrix, you can also view this as when you multiply A to A inverse in left, either from left or from right, you get the identity matrix. Therefore, A itself should be the inverse of A inverse. Is that clear? Okay. How about the second one? If you multiply a non-zero scalar to any non-singular matrix, take note that we should be multiplying only non-zero. If you multiply a non-zero scalar to every entry of a non-singular matrix, the resulting matrix is also non-singular. In fact, the inverse of the non-singular matrix R times A is the multiplicative inverse of R times the inverse of A. Take note that this R inverse denotes the usual multiplicative inverse as if we're doing it in the standard number system. For example, if A is non-singular, then we can say that the matrix 2 times A is also non-singular, And its inverse is going to be 2 inverse times A inverse, or you can write it as 1/2 times A inverse. However, A inverse, as I have already mentioned before, cannot be written as 1 over A, so be careful about that. The reason for this is the fact that when you multiply RA to R inverse times A inverse, using properties of matrix multiplication, these two scalars combine. As you can see, this is going to be 1, this is going to be the identity matrix, so the resulting product is the identity matrix. Similarly, if you multiply R inverse A inverse with RA, you also get the identity n by n matrix. This is why this matrix should be the inverse of R times A. The third property is about the product of two non-singular n by n matrix. The product of two non-singular n by n matrix, A times B, should also be non-singular if A and B are given to be non-singular. Take note that the inverse of AB is equal to B inverse times A inverse, and not necessarily A inverse times B inverse. Remember, for matrix multiplication, the order in which we multiply matrices is really important because matrix multiplication is not in general commutative. The reason for this equation is the fact that when you multiply AB with B inverse times A inverse, you see by associative property, we can associate B and B inverse like so. This gives us the identity, but the identity doesn't do anything there. It just gives us A inverse, and this is going to be IN. And similarly, or in a similar fashion, we can write B inverse A inverse times A times B, and this, as you can see, will also reduce to the identity n by n matrix. This is why B inverse times A inverse is the inverse of the product A times B. Take note that in general, I'd like to write this because this is important. The inverse of the product AB is not the same as the inverse of the product A inverse times, the product of the inverse is A inverse times B inverse. This is because of the fact that when you multiply AB with A inverse times B inverse, you just cannot do anything about this one because one cannot just switch the positions of B and A inverse to cancel the matrices. Property number 3 actually generalizes to any number of matrices. So if I have matrices A1, A2, AK, for example, I have K matrices over here, or all of them are m by n, and all of them are non-singular, okay? Then the product A1, A2, AK is also non-singular. This is done by induction. In fact, in this case, the inverse of the product A1 up to AK is going to be in the reverse order. The inverse of AK times the inverse of AK minus 1 and so on times the inverse of A1. Last but not the least, if you are going to replace each one of these by the same matrix A, you get A to some power, let's say n, no? I think I should not be using n here because the n is reserved for the size of the matrix. Anyway, if this is, let's say, some exponent k, no? That is accomplished by simply setting each one of these equal to A. So this is A to the k inverse is going to be k times, or multiplying A to itself, multiplying A inverse to itself k times. That's why we have the following on the right hand side. Anyway, let's continue. So I have a question over here. If I get two n by n non-singular matrix, did I get the sum, or can we also guarantee that the sum is non-singular? The answer is apparently no. As a quick counterexample, you can consider the identity matrix In, which is known to be non-singular, and the matrix minus In, which is also non-singular because minus In is just the product of -1 times In, and this is not 0, right? So these matrices are non-singular. However, if you add these matrices, you get the 0 n by n matrix, which is a singular one. So we cannot guarantee that if A and B are non-singular matrices, we cannot guarantee that their sum is also non-singular. Now, what benefit is there when we know that A is non-singular? One of the benefits that uh, we are enjoying whenever we have a non-singular matrix is the solvability of a linear system, in particular an n by n linear system. So this is a square linear system. A times x equals b. For this, take note that I can multiply on the left A inverse, and then I have the following. I'm sorry, I think something is missing here. I think there should be A inverse times b. From this equation, I multiplied A inverse on the left, and it became like this. Then here, I use associative property to associate the matrices A inverse times A. And then, get the following as the result. Because In is the identity matrix, In times X reduces to X only. And therefore, we have a solution for X, namely A inverse times B. Therefore, as a conclusion, the linear AX equals B has a unique solution X, which is equal to A inverse times B. Take note that this generalizes the fact now when we are studying the real numbers now, whenever you have the equation AX equals B and A is not 0, do you remember this? Then we can conclude that X is A inverse times B, or dati, before, this one is written as B over A. But remember, we don't do divisions when we talk about matrices. So we state it in the form of a theorem. It states that if A is non-singular, then the linear system AX equals B has a unique solution X. This should be BX. I'm sorry, that's typo error. A inverse times B. To illustrate, let's consider this 2 by 2 linear system. Equivalently, we may write it as AX equals B, where A is the square matrix 1, 3, 1, 4. So this came from, or this was extracted from the coefficients of the left-hand sides. Then the matrix X is actually a column vector XY, column of unknowns, and B is also a column vector 5, 7. Take note that this is non-singular, as we have already seen in the previous example, and its inverse is equal to this. So once you know that the inverse of A is this, then we can conclude that this unknowns xy, which is the column vector x, is equal to A inverse times B, as it was written in the theorem now. And the inverse times B is this. Now, so once you know that that A inverse, then x and y are already known. The product can be obtained by simply multiplying rows by columns, remember? Taking the dot products of rows and column. First row, first column, you get this. Second row, first column, you get this one. Alright? So, therefore, whatever numbers or whatever scalars you put in place of 5 and 7, this linear system will always have a unique solution because the coefficient matrix A is non-singular. So that's the idea. Let's now talk about a linear system that is really important. So We say that a linear system is homogeneous, or a homogeneous linear system, if the constants on the right-hand side of every linear equation is 0. Take note that if the coefficients are always 0, this is always consistent, or it always has a solution, because the zero vector, the zero column vector, is always a solution. I mean, when you put the zero column vector over here, no matter what A is, no, the result is always a zero column vector. The solution, which only has zeros as its values for the unknowns, no, is called the trivial solution of the homogeneous linear system. Again, take note, a homogeneous linear system always always has a solution, namely the trivial solution. So it's not really a question of whether this has a solution or not, because it always has a solution. The question that we wanted to ask, if we have a homogeneous linear system, is if there is a non-trivial solution. So that's what we are after too. So is there a solution that is not zero? Or can we find a non-zero x so that this is equal to 0? So that's really the problem in this case. Also, I want you to observe that if x1 and x2 are solution vectors to this linear system, then so is the sum x1 plus x2, meaning to say, if you get two vector solutions to the linear system, to the homogeneous linear system, you add these solutions component-wise or entry-wise, however you want to call it. The resulting vector is also a solution. This is really because when you multiply a to the sum x1 plus x2, by distributive property, you get the following. Because each of x1 and x2 are solutions, these things are zero columns. Therefore, that's 0. Take note that the 0 here is not the 0, the number, but rather it represents the 0 vector, or the 0 column vector. Also, when you stretch a solution vector by a scalar factor of r, the resulting vector is also a solution. For example, if x1 is a solution, multiply it by 2, multiply it by 3, by -5, by 4/5, by pi, no, if you want. The resulting solution, the resulting vector is also a solution. For the same reason that when you multiply a with rx1, this is the same as r times a x1, because r is a scalar. And this one is going to be the 0 column vector, and therefore that's 0. As an example, let's find the solution set for this linear system. So we again employ the Gauss-Jordan algorithm. I am going to do the computations for you. So the resulting REF is this matrix. So this is the column corresponding to x, y, z, and w. Then we can describe the solutions as follows. X plus 2z equals 0, y minus z equals 0, and w equals 0. As you can see, x, y, and w are what? They are called leading variable. On the other hand, the column that doesn't have a pivot or a pivot is called a free variable. So over here we have z as the free variable. Therefore, this has infinitely many solutions. Therefore, for this case, the homogeneous linear system has a solution aside from the 0 or the trivial solution. In fact, to write the solution in general form, we get the following. So here I set the free variable z to r and get the following as the general solution, where r is a scalar, or you can actually write it as r times the vector minus 2, 1, 1, 0. So therefore, every solution to this linear system is just a scalar multiple of the vector minus 2, 1, 1, 0. Alright? In fact, we can write the solution set as follows. So as you can see here, this has a non-trivial solution because it has what? it has infinitely many solutions. So the real deal about this problem is that because the right-hand side of every equation are 0, then it is expected that if we just place zeros for each one of these, for each one of the unknowns, then it is really a solution. What interests us are those solutions which are not really or not necessarily the zero vector. For example, in the case of minus 2, 1, 1, 0. This is not really the zero, or this is not to make this equal to 0, yet the right-hand side remains 0. Okay, let's move on. In fact, when you have a homogeneous linear system with fewer equations than unknowns, you get that? Fewer equations than unknowns. For example, 3 by 4, 2 by 29, 5 by 74. No? These are homogeneous linear systems which has fewer equations than unknowns. Then automatically this linear system will have a non-trivial solution. The reason for that is because when we have, let's say you have a 5 by, let's say this is 5 by 7, no? If you have a 5 by 7 linear system, then because we only have 5 rows in this equation, so there is a maximum number of pivots. So the maximum number of pivots should be 5 because there are only 5 rows. And because there are 7 columns, if you have maximum number of pivots, that's the same as the maximum number of hidden variables, 5. Therefore, there are at least two free variables. So always, this linear system will have at least two free variables. Therefore, we'll have infinitely many solutions. So aside from the trivial one, we will get to have a non-trivial solution. That's why the theorem actually holds. You can just generalize it or look at it in a more general way. So let's now continue. Let's now continue defining the so-called elementary matrix. These elementary matrices are important tools in studying non-singular matrices because, as you will see later, these are actually the building blocks of non-singular matrices. Elementary matrices generalize the so-called elementary row operations when we were studying Gaussian elimination before. Because there are three types of elementary row operations, as we can expect, there are also three types of elementary matrices. So let's read the definition. So an elementary matrix is just a matrix which is obtained from the identity matrix by performing a single elementary row operation. So first, we begin with the identity matrix. Apply any row operation for that matter. So you have plenty of options, right? So if you perform a single elementary row operations on the identity matrix, the resulting matrix is called an elementary matrix. So basically, IN is the default. When you try to modify it once, no, by an elementary row operation, the resulting matrix is called an elementary matrix. If you have obtained the elementary matrix by doing a type 1 operation, the elementary matrix is said to be of type 1. If, on the other hand, you perform a type 2 operation instead, the elementary matrix is type 2, and so on. Right? For example, the following matrices are elementary matrices. Yeah, because this one was obtained from the identity. This is the identity. I did a row swapping, right? So this is a type 1 elementary matrix because I swapped the first row and second row of the identity 2 by 2 matrix. This is also an elementary matrix of size 3 by 3, but then this time it is a what? um, sorry, this is a type 2 elementary matrix because from I3, I multiplied a factor of 2 on the second row, right? Last but not the least, this is also an elementary matrix. This was obtained from the identity 3 by 3 matrix by doing the following operation. This is a type 3 operation where from the identity, we replace the first row by its sum to negative 5 times the third row. That's the notation. Remember, do you remember this notation? Again, this one was obtained from I3 by multiplying the second row by 2. This was obtained from I2 by just swapping. For this reason, this matrix will be denoted by the name of the operation that we have performed. So we shall denote this matrix as the matrix E12. Of course, the size should be specified in advance. 2 by 2 in this case, these ones are 3 by 3. So a 3 by 3 matrix, elementary matrix of this form will be denoted by E2 parenthesis 2. And a matrix of this type will be denoted by E13 minus 5. Now take note that uh, to not be confused with how we uh, manage to write this elementary matrix, whenever you perform E13 negative 5, you just write the identity matrix once more, and then look for the 1, 3, and 3. Here is the 1, 3, and 3, and then just place minus 5. So that's the technique, or that's the shortcut. So these are the notations that I'm talking about. If a matrix was obtained from In by interchanging rows I and j, where I is not j, that matrix will be denoted by Eij. Type 2 matrix. If a row I is multiplied by alpha, the resulting matrix from the In will be denoted by Ei alpha. Type 3. So if a type 3 operation of this form is obtained from the identity, then it is denoted by Eij alpha, like what I have told you. For example, this matrix is the E13 matrix in the space M sub 3, right? 3 by 3. Because this was obtained from the identity by swapping the first and the third rows. This is the identity when the first row was multiplied by minus 3, as you can see. And this is the identity matrix when the operation E234 is performed. Again, as a technique, you don't have to perform the operation really. You just have to draw or construct the identity matrix once more and then look for the 2, 3 entry, which is this, and just place a 4. That's the shortcut. So let's look at this 3 by 4 matrix. So this matrix has 3 rows, right? If I multiply the elementary matrix E13 to A on the left, like so, this is the E13 matrix times A, we should be getting, or you can verify that this is going to be the resulting product. What do you observe? You can pause if you want to think about this one. Anyway, if something's going really fast, you can pause and rewind. So what do you notice in this example? Yeah, so this is the original matrix A. No? What happened was that this is just A when the first row and the third row are swapped. Do you notice that? In other words, the effect, now basically this one, the E13, again, let me draw a diagram for you. If I3 was transformed to be the E13 matrix, This is A. If you multiply E13A, this transformation or this arrow is just E13. Meaning to say, if E13 was obtained from I3, or this elementary matrix was obtained from the identity by swapping the first and the third row, then if this matrix, when you multiply it on the left, on the left of a given matrix of the same number of rows, then the resulting matrix was obtained by simply performing a type 1 elementary, the same type 1 elementary row operations as how you get this from the identity. As you may have suspected, if you multiply the elementary matrix E1 negative 3 to the left of A, you should get the following as the product. Oh, I'm sorry. These are wrong. I think these are minus 3. Minus 3, minus 3. I forgot the minus sign. So what happened was that minus 3 was just multiplied on the first row. You can verify, no? Paano ba nag-multiply? Rows by columns. Rows by columns. Rows by columns. Or you can then make this table, no? If you want. Yung tinuro ko sa inyo before, no? You can set up this table if you want. And then have this as the resulting product. Finally, if E234 gets multiplied to A, ito siya, no? We get the following as the product. So same thing has happened, no? Kung paano mo na-obtain ito from the identity, when you multiply it on the left of A, yun yung gagawin niya sa A. Yung same operation ang gagawin sa A. This observation leads to the following, no? If A has n rows, and you perform an elementary row operation on A, obtaining a matrix B. If E is the elementary matrix obtained from IN by performing the same elementary row operation, then B is actually E times A. Meaning to say, if E was obtained from the identity by performing a certain elementary row operation, then when E gets multiplied to A on the left, obtaining a matrix B, then B is just actually A when this elementary row operation was performed. Therefore, if a matrix B is row equivalent to A, again, what do you mean by being row equivalent? B was obtained from A by simply doing a number of elementary or row operation from A to obtain B. Then each row operation corresponds to multiplying an elementary matrix on the left, right? For example, E1 represents the first elementary row operation that you performed. EK should be the kth elementary row operation performed. If the resulting matrix is B, then you can write B as the product A. So we're going in the left direction, to the left direction, in the direction of towards the left, no? Reverse. A, then the first operation was performed, and so on. Kth operation was performed, obtaining a matrix B. I want you to observe an important fact, no? That elementary row operations are actually undoable or reversible. What do I mean by that? If you somehow, so Eij is obtained from the identity by swapping row I and row j. If I again swap row I and row j, that corresponds to multiplying Eij again on the left, no? Again, for example, you swap the second row and the fourth row, and swap again the second row and the fourth row. What is the result? The result is just the identity matrix. As a result, this means that Eij, no, the matrix Eij, is non-singular, and its inverse is itself. Okay? On the other hand, this means that if you somehow multiply a row I by alpha and then multiply alpha inverse on the same row I, that cancels the operation and that will give us the identity matrix. Finally, if you do a type 3 operation Eij alpha and then you do the same, you do another type 3 operation Eij minus alpha, ito yung additive inverse, type 3 operation Eij minus alpha, then you will get the identity matrix. Let me quickly show you what's really going on over here. It's like, for example, I have 1, 0, 0, 1. Okay? If let's say I perform E1, 2, negative 2. If I perform E1, 2, negative 2, I'll be getting 1 minus 2, 0, 1. Now, if I somehow perform E1, 2, 2, I'll just change the sign of this one, what will happen? What happens is that may eliminate ito from here. Okay? So what happens is that babalik ka sa identity matrix. What I'm saying is that E12, the E12 matrix, no? Ang may E12 negative 2 na matrix, ito siya. 1, negative 2, 0, 1. Yung E12, 2, 1, 2, 0, 1. If, as elementary matrices, if you try to multiply this, if you try to multiply them, if you try to multiply these things, you should be getting the identity. What I mean to say is that 1, 0, 0, 1 at ito yung magiging I2. That's what I really mean to say. So it's like whenever, what we have discovered at this point is that whenever we are performing an elementary row operation, we are actually multiplying an elementary matrix on the left. This is just actually matrix multiplication on the left by an elementary matrix. At first, this is quite confusing, but you can actually make sense of this when you try to read it again and again. An elementary matrix is usually non-singular. No, it's always non-singular, I'm sorry. And its inverse is going to be an elementary matrix of the same type. To summarize, if you have a type 1 operation, the inverse of Eij is also Eij kasi doing the same Eij operation reverses the job. If you want to do or reverse a type 2 operation, you just do the same type 2 operation, but then you have to multiply the multiplicative of alpha instead. That's why alpha here should not be 0. At pangatlo, when you have the type 3 operation Eij alpha and you want to do the reverse that, somehow reverse that can be reversed by performing Eij minus alpha. So for type 2 multiplicative inverse, for type 3 additive inverse. Okay? Please remember these formulas as this will become useful later. As a result, corollary to the previous theorem, not this one, but the theorem in the last slide, if B is row equivalent to A, meaning B is obtained from A by performing a sequence of elementary row operations, then what happens is that you simply have performed a sequence of elementary row operations, meaning you've multiplied elementary matrices on the left of A, successively obtaining a matrix B. That's what we really mean by that. Because each one of these is non-singular, this one is non-singular as well. The product of non-singular matrices is non-singular. So you can take this as your matrix P. That's why as in the corollary, there is a matrix P, a non-singular one, so that B is equal to P times A. So, the thing is, whenever B is obtained, kapag pala ikaw ay nagro-row reduction, no? Transforming A to a certain matrix B after a sequence of elementary row operations, ang nagko-connect pala, no? So, the thing is, ang nagko-connect pala from A going to B is a non-singular matrix P. Ang nagtatawid pala from A to B is just a non-singular matrix P. At yung P na to ay binubuo ng mga elementary matrices. In fact, we have a more general theorem for that. So the following are equivalent statements. When we say that the following are equivalent statements, this is not to say that each one of these is true. No. What we're saying is that if one of these is true, then all the rest are also true. If one of these is false, then every one of these is also false. You understand? So, how do we prove that the following are equivalent statements? Well, we have to show that each one of these statements imply one another. One common technique is to find a cycle of implications. What do I mean by that? So, for example, in this theorem, we will be proving that 1 implies 2, 2 implies 3, 3 implies 4, sorry, again, 1 implies 2, 2 implies 3, 3 implies 4. Then I will prove that 4 implies 5, and eventually 5 will imply 1 back. Whenever I do this, no, as you can see, this by hypothetical syllogism, each one of these statements will imply one another. This is one common technique. But take note that the implications 1 implies 2, no? If A is non-singular, this linear system has a unique solution, is already established a while ago. No? Also, if Ax equals B has a unique solution, then this homogeneous linear system has trivial solution. Also follows, no, from the fact that if we simply set B equal to 0, no, kasi may kulang sa statement 2, this should be for all column vector B. So in particular, if you set B to 0, then because this has a unique solution, no, the only solution for the homogeneous linear system is the trivial solution. Okay? So what we are after to in this theorem or in the proof is we're going to prove that 3 actually implies 4. RREF pala ng pag pala ito'y totoo, ang RRGF ng AIIN, pag pala ito'y totoo, kapag pala ito naman ay totoo, ang RRFIIN, si A ay product ng elementary matrices. At kapag ito'y totoo, si A ay non-singular. So what we have learned in the theorem is that there are many ways to rephrase the definition of being non-singular. No? These are all characterizations or necessary and sufficient conditions for a matrix to be non-singular. It's like, for example, non-singular kung RREFIN. Non-singular, kapag product ka ng elementary matrices, non-singular ka. In fact, lahat ng non-singular matrix ay product lang naman ng mga elementary matrices. Yung number 5 as a highlight shows that elementary matrices are actually building blocks of non-singular matrices. It's like similar to the fundamental theorem of arithmetic, no? Every integer n greater than 1 is just a product of prime numbers. Similar, if you have a non-singular matrix, then it is simply or basically a product of elementary matrices. Okay? So here we are proving 3 implies 4. So 3 is written on the board, we're proving 4. We are going to prove that if Ax equals EOS only has a trivial solution, then the RREF of A is IN. So assume that this is, so I think this is capital X. Assume that Ax equals 0 only has a trivial solution. We're going to prove that the RREF of A is not IN. So we're proving this indirectly. Suppose that the RREF is not IN. then the RREF necessarily has fewer than n pivots. And as a consequence, if you have a fewer than n pivots, then necessarily this RREF should have a zero row. Okay? Hence, the linear system AX equals 0 has a non-trivial solution because if you have a zero row and then on the right hand side you have 0, this reduces to a linear system that has fewer equations than unknowns because um, the last row was turned into a zero, all zeros, right? Therefore, AX equals 0 has a non-trivial solution. But this contradicts the assumption. Therefore, the RREF should be the identity. Let's now turn into proving that statement 4 implies statement 5. Suppose that or assume that the RREF of A is the identity matrix. We're going to prove that A is a product, or we're going to prove that A can be factored as a product of elementary matrices. So assume that the RREF of A is IN. How do we show that A is a product? Well, when we say that the RREF of A is IN, this is the same as saying that A can be reduced by performing a sequence of elementary row operations to A to get IN in the end, right? Now, each one of the elementary row operations correspond to an elementary matrix being multiplied on the left of A. So therefore, eventually, if this elementary matrices gets multiplied to A, eventually you will land on the identity matrix. Now here, this is very important because it tells us how to write A as a product of elementary matrix. So if it happens that these are the elementary matrices, then thinking of this as a single matrix, you have, let's say, P times A equals IN, right? We can multiply P inverse on the left, yeah? So I get A as P inverse. So ito yung P inverse. But remember, we're doing it inverse should be done in reverse order. Ito yung tinatawag na shoes and socks property. Diba? Baligtad. Kung ano yung unang pinasok, yun yung huling ilalabas. Shoes and socks property. Alright? Now remember that inverses of elementary matrices are also elementary matrices, in fact, of the same type. Therefore, A is a product of elementary matrices because these matrices are also elementary. So, paano mo isusulat si A as a product of elementary matrices? Yung unang operation na pinerform mo, take the inverse. Yung unang pangalawang elementary matrix, take the inverse, and so on. Finally, to prove that 5 implies 1, if we assume that A is a product of elementary matrices, then A is non-singular. This is the easiest one. Because if A is a product of elementary matrices, and since elementary matrices are non-singular, then A being a product of non-singular matrices is also non-singular. And that completes the proof. So this gives us the following theorem. So let me illustrate the theorem in the following example. So suppose we wanted to show that this is non-singular. We wanted to find its inverse, and we wanted to write A as product of elementary matrices. How do we do that? Well, we attach the identity 2 by 2 matrix over here and then do Gauss-Jordan method, but this time we will take note of the operations that we need. So if I apply E12, we get the following. So I'll see that the rows have interchange. From here, I have a pivot. I have to eliminate that. So I apply this type 3 operation. E21 to 1, negative 3, and get the following as a result. Next, I want this to be a pivot. Now I want this to be a pivot, so I multiply a negative 1 on the second row, obtaining the following. And finally, I have now a pivot over here. I just want to eliminate that. So I apply a type 3 operation E1 to 1. So there. So it happened to be, the left-hand side happened to be the identity matrix. Therefore, the resulting matrix is non-singular. I want you to take note of these operations. Parang sa theorem, ito yung E1, ito yung E1, ito yung E2, E3, E4. So we have performed 4 elementary row operations. So A is non-singular and its inverse is that. And sabi, write A as a product of elementary matrices. Eto na. So si A basically ay si identity obtained from A by performing a sequence of 4 elementary row operations, namely E12, E21 negative 3, E2 negative 1, and E12 parenthesis 1. Ito yung E1, E2, E3, E4 sa theorem. Kukunin natin si A. Paano? Isipin nyo, P ito. And then, multiply P inverse on the left. This reverses the order. O, diba? Magiging ganun yan. So, E12 inverse, E21 minus 3 inverse, E2 negative 1 inverse. Magbabaligtad ang order, ha? Alright. Remember that the formulas for inverses of elementary matrices, the inverse of E12 is itself because it's type 1. Diba? Ang inverse ng E21 minus 3, type 3, just change the sign. Nasa parentheses. Pag type 2, just get the reciprocal. Kaya lang ang reciprocal ng negative 1 kasi 1 over negative 1 is also minus 1. So type 3 ulit, E1 to 1, magiging E1 to negative 1. Now writing them as matrices, ito siya. Ito si A, no? Yung E1 to, ito. Okay? Si E21 negative 3, type 3, ito siya. Si E2 parenthesis negative 1, ito siya. Second row gets multiplied to minus 1. And E1 to negative 1 is this thing. Now, if you want to verify if you get the correct answer, let's go copy this from scratch. So we wanted to multiply, wanted to multiply 0, 1, what was that? 0, 1, 1, 0, 2, sorry. Let me draw a long vertical line over here because I wanted to do something. And then second matrix is 1, 0, 3, 0. 1, 0, 3, 0. So what's the product? The product is, this is 3, this is 0, this is 1, this is 0. So that's the resulting product. Then we will multiply, what? Ito na tayo. Pangatlo na tayo. 1, 0. So product na ito, yung multiply ito sa kanan. 1, 0, 0, negative 1. Dito ko lalagay 1, 0, 0, negative 1. Ito kasi yung product ng dalawa. Ito kasi yung product ng dalawa na pag mag-multiply pa ako ng isa pa sa kanan, dito ko nalalagay. Multiply, 3, 0, I think it's 0, 0, 0, right? 1, 0. Oh, may mali yata ako. Did I... Yeah, ganyan lang siya, no? Did I do it correctly? At ang last matrix, 1, negative 1, 1. Ganyan. If I multiply, this is going to be 3, negative... Oh my gosh. I think I did something wrong. Yeah, I saw my error. Nakakainis. So, ito yung mali. Mali ako dito. Ulit. Ito yung mali. when you look at this closely, may kulang dito. Ang kulang dito ay 1. This should be a 1. Now, yung E213, that should be a 1. I'm so sorry. Okay? Alright. So, let me change that now. What's that? 1031. What? Tama ito. 103, sorry. 31. So, let's redo the calculation once again. I thought something is really odd. So let's do the computation once again. This is 3, this is 1, that's 1, this is 0. Then this one, this is 3, this is minus 1, that's 1, this is 0 once again. And then this is 3, negative 4, 1, 1, negative 1. Yeah, correct, no? As you can see, as you can tell, this matrix is the given matrix. So really, we have confirmed that this is the product. A is the product of these elementary matrices. I'm sorry for this careless error, but at least we have seen where the mistake was done. So we have to cut this video at this point, and we will continue next time. If you have questions, you can send email to me, okay? An email to me. Thank you for listening and study hard.